Alrighty, today we are going to be talking about topic 1.12, function transformations. So, when we have a function, let's say we have f of x, right? This here is f of x. We can manipulate this f of x here in different ways in order to move the function, to dilate it, and yeah, we can dilate it, we can move it, we can flip it, reflect it across axes. But how do we know what we're doing? How do we know when that happens, what it looks like, and how do we decode this thing? Right? So the first thing we have to understand is what each type of translation is. So our first translation is vertical. Let's say A. So when we have our function, and then outside of the parentheses, we have plus or minus A, just some number, then that means we are translating vertically. So if we are plus, let's say we're plus 3, right? Then this function would be up here now. Everything else is the same. It's just up by 3 units. And how that works is all the processing goes on in here. X is times something or whatever. Whatever happens in the function happens in here. And then whatever the answer is, add 3 to it. So whatever goes on down here, I don't care. As long as we add 3 to it, that's fine. Now, for our second type of transformation, we have horizontal. Now, inside the parentheses, adding or subtracting, let's say minus 3. Adding or subtracting a value inside the parenthesis, directly to the x. Now, what this does is you translate the graph by whatever this is, but negative. And one thing to always remember is that horizontal translations, dilations, whatever, if it's horizontal, it's going to be wonky. It's going to be not exactly how it's written. So it's minus 3. In this case, it's plus 3 because horizontal translations are backwards. They're negative version of what's on here. So it says minus 3, so you'd think it goes back here. But actually, since it's horizontal and it's flipped, we're going to go just like that. Just 3 units to the right. So our third type of alteration is going to be a vertical dilation. Wrong color. And vertical dilations are on the outside. So let's say 5. 5 times whatever's in the parentheses, right? So in this case, what happens here is whatever the answer is, we multiply it by 5, which gives us a really amplified version of the function. So higher highs, lower lows, you just take y value is, your elevation, and you multiply it by that number. So let's say this is a point at y equals 1, multiply it by 5, it's y equals 5 now. Do that with every other thing in the graph. And we'll do more examples with that later, but just know that you multiply the y by the y dilation, or by this number, outside the parentheses, multiplying the function. Now, if we want to dilate horizontally, we are going to multiply directly to the x inside the parentheses. So let's say 2x. Right? And remember, horizontal anything is always going to be weird. In this case, instead of being negative, it's going to be, instead of multiplying by 2, you're going to divide by 2. Or in essence, it's just times 1 over 2. Now, how this works is, imagine the number, this number right here that you're multiplying directly to x, as the speed, right? So if this is a normal function, right, we're going like this, whatever, and we go like that. If we increase the speed, then that means we are reaching these points faster. We're reaching them sooner. Let me put that in a different color for you. So normally we would reach this a lot later, but instead we're going a lot faster. We're going straight up. We're just doing things much quicker. But we're doing it in less space. So what you do with the numbers in the coordinate plane is that this right here moves back horizontally. So numerically it's 1/2, but in terms of in the function it's 2 because you're 2xing the speed that it goes up and down. And then same the other way around. So if you were to have, let's say, x over 2 instead, then it would go slower. Different color. It would go much slower, but it would take up more space. You get what I'm saying? That's why it's the inverse. That's why it's 1 over 2 instead of 2, or it's 2 instead of 1 over 2. Like in this case, in the function, it's 1 over 2. But in the graph, it takes up more space, so you multiply each point by 2 to get where it is. So remember, this number multiplying directly to the x is the speed. If we have a lower speed, we take longer to reach each point. And therefore, we take up more space. So the smaller numbers, the reciprocal is actually bigger. So you multiply this x value, because remember, we're only horizontally dilating. You multiply this x number by whatever the reciprocal is. So, and we'll do more examples about this later, but it's just kind of how that works and how to think about it. But yeah, I'll erase this. 2x if we were to dilate horizontally, 2x if we were to dilate it. Because 2 times the speed, which means we reach this faster, and then we just go like normal. We reach it faster, and then we go like normal. Faster takes up less space. Right? And then our final 2 are reflections. If you make this negative, if you make the x negative, then you're reflecting across the horizontal axis. Or you're reflecting horizontally. So you're reflecting across this y-axis. You're flipping it horizontally. So imagine you have a hinge, or like a point of rotation that is making it go horizontally. So it's facing up, and then it's rotating around. And then the other way around is if we were to make the function negative. In that case, we are going to flip it over the x-axis, which I realize looks exactly the same, but we're bringing it over. Right? So that is how those work. And now I have an example here. So first thing we're going to do before we do any translations, before we figure anything out, is we are going to figure out what translations we actually need to do. So I'm just going to bring this aside. So if we look at this, the most easily identifiable thing is this right here. Vertical translation. It's outside, just adding or subtracting from the giant function mess right here. So we are vertically translating up, because this is positive 1 by 1. Right? And okay, let's look at this. Now we have a we have a vertical dilation right here. So this 2 is a vertical dilation. And we are dilating by factor of 2. Now let's go into this function here. X over 2, that is a horizontal dilation. And it's tempting to put by a factor of 1 over 2, but you have to remember, this is the speed the dilation factor is the distance. So if you're going at a lower speed, that means you have to change it, you have to flip it, so that way you're going for a longer distance. So it's actually 2. And then finally we have our horizontal translation. And it's tempting to put -3 here, but you always have to remember, horizontals are weird. So you want to flip it so that it is just 3. 3 to the right. So, in practice, what does this look like? Well, there's a specific order we have to put these translations and dilations in. Okay, so let's start inside of our parentheses here. So we'll always start with dilations. Dilations are always first. So let's do our horizontal dilation first. Factor of 2. So we're going to take this 3, and keep in mind this graphing plane, every 2 units is 1, which made me mess up earlier. So we're starting at -3, and we're going back to -6, which is right here. And the reason we're doing that is because we're taking this number and we're doubling it. Horizontal dilation of 2. So we're doubling this -3, getting -6. So after we do that, horizontal dilation is done. Still in the parentheses, we are going to do the horizontal translation. So we're going to go to the right by 3. So we're going to go 1, 2, 3. Well, this is 2 per unit, so really it's 1, 1, 2, 3. So really, you end up right back where you started because of that translation. So we're going to do our vertical dilation. So we're going to multiply our y value by 2 because we're doing it factor of 2. So multiply this, 3 up, it's 1.5. We multiply it by 2, we get 3. And then after we do that, let me just erase this point here. Our final step is the vertical translation. So vertical translation, up by 1, up by 1. And I'm going to put this in green because this is our final point. So this point here has translated back horizontal dilation, horizontal translation, vertical dilation, vertical dilation, vertical transformation. And then we ended up here. And now we have to do the rest for all the points, but it doesn't take too long. So we're going to start here, -2, dilation, we double it, go to 4, and then we add 3, we go to 1, and then we double our y, so we go up to 3, and then we add 1, so we go right here. Doink. And we continue. So we start here. Horizontal dilation, 2 times 0, doesn't matter. And then we have our translation, so to the right by 3. So we go to the right by 3. And then our vertical dilation, so we go up to here, and then our vertical translation, so we're right here. Now this point right here, we are going to do our horizontal dilation. So we start at 1, we double it, we go to 2, and then we add 3 because of our horizontal translation. So 2 goes to 5. We do our vertical dilation. So we double what we have, we go up to 1, and then we add 1 because of the vertical translation. So we go up by 1. And I just realized that I've been only going up by 1 unit, not by 2, because this graphing plane is 2 per. So I'm actually going to move these up by 1. Same thing still applies. I didn't say anything wrong. I just didn't account for the two grid spaces per number. And then our final point here, might even go off the side. So we have our point at 3.5, goes up to 7. 7 is right here, and then we add 3, so we're all the way out here. And then we do our vertical, we do our, yeah, we can't see it. That's okay. My graph making skills are not perfect. One thing I also like to do is get the bottom of the circle, so I really know where it is. So we're gonna translate that as well. So we're gonna do horizontal, double that, and then we're going to add 3, get to 1. We're going to do our vertical, we're going to double it, we're going to get to, let's see, how much is that? It's up to here, because we double 1.5 tiles, and then we get 3 tiles, and then we're up here, and then we add 1, so right there. Put our little dot, and now we can draw our lines. And then there's one that goes off into the distance. And that is our finished product. Now, I hope this helped out. I know there's one other thing that was important about this lesson that I may not have covered yet. No, it doesn't look like it. When you have a table, what you want to do is, let's say we have a table with this function right here. Just pretend I got everything first try there. Say we have a table with this whole monstrosity here, right? And we have our different values. So let's say 1, 2, 3, 4, 5, and then A, B, C, D. So I'll add a 0 for good measure. C. So if we are given and told, okay, what is f of 6? What's f of 6, right? Then the really intuitive way to solve this is go, okay, well, 6 over 2 is 3. 3 minus 3 is 0. And then, so this is 0. 2 times 0 is 0, and then 0 plus 1 is 1. So it's 1, right? But you forgot about the f. F. So really, what you end up with is, yes, 6 over 2 is 3. Minus 3 is 0. But you end up with f of 0. F of 0, this is a table of f of x. F of 0 is equal to z. So really, you end up with 2 times z plus 1. And let's say z is equal to 5, right? Let's say this is 5. Then it's 2 times 5 plus 1. 10, 11. So f of 6 is equal to 11. Important distinction to remember. But that'll be all. If there's anything I missed, anything you want me to cover, please let me know. But hope you enjoyed.